Just because a planet can support life, does that mean it will? Here on Earth, the chemistry of life relies heavily on the element carbon. Carbon is one of the most versatile elements. Each carbon atom can hook up with 1, 2, or 3, or 4 other atoms. It can even link up with other carbon atoms, creating long chains or rings. Throw in a few other elements and you've got amino acids, the ingredients of proteins, the building blocks of life as we know it.
Carbon is a very useful element to sit at the center of life's chemistry. There's a lot of it in the universe. It's made very easily in stars. It makes very complicated, meshed together compounds which have the possibility of changing each other's properties. You can have a really complicated, complex setup with carbon. I'd expect that very nearly all life forms we come across that are matter-based are going to be carbon-based.
If carbon helps make life happen, then there might be a lot of life out there. Carbon is one of the most common elements in the universe.
Hi, it's Mr. Anderson, and in this podcast, I'm going to talk about polymers. Polymers are large molecules that are made up of smaller molecules called monomers. And so even the word polymers can serve as a good example of a polymer. In other words, I could rearrange the letters in polymers to make Mrs. Polly, or even a spry mole, or even a spine mushroom. And so basically, those letters can be arranged in different ways to make different words. Likewise, monomers can be arranged in different ways to make different polymers. And so the large molecule is a polymer, but those building blocks are called monomers. And so where do we see this? Well, in biology, we could see this lots of places. And so this right here is a strand of cellulose, and cellulose is a polysaccharide, which is made of sugar over and over and over again. Or this right here is a protein. Protein is made up of amino acids that are attached over and over and over again. And so we have 26 letters in the alphabet, and we can make words, and we can make paragraphs, and even stories. And in life, we have 20 amino acids, and those amino acids can almost make an infinite number of proteins. Or this right here is deoxyribonucleic acid, or DNA, and that itself is made up of monomers. Those are called nucleotides. Essentially, we've got a phosphate, a sugar, and then a nitrogenous base. And so even that nice leisure suit that your dad may have worn in the 70s is going to be a polymer. In other words, we're reproducing this simple chemical over and over and over again. And so how do we do that? Well, basically we do it in one of two ways. We either build a polymer, and to do that we use what's called a condensation or a dehydration reaction, or we break it down. And so let's start with building. And so right here we have two amino acids. And so amino acids, remember, are going to be put together to make proteins. And so you can see on this first amino acid, we've got that alpha carbon in the middle, we've got an amino group on one side, carboxyl group on the other. Likewise, with this amino acid, we've got an amino group on this side, we've got the carboxyl group on this side, and then we have our R groups on either side. And so basically what happens in a condensation or dehydration reaction, if you look right here in the middle, is that we're going to remove water. In other words, we have this hydroxyl group here and this hydrogen here. And so basically what happens is we give off that water. You can see why it's called a dehydration reaction. We're losing water. And basically we're forming a bond. We're forming a bond between those two amino acids. In other words, we're making a simple little polypeptide. And this occurs over and over and over again when we make a massive protein. Well, what's the opposite of that? We call that hydrolysis. And I always think of hydrolysis means water cutting or water breaking. And so let's say right here we have a simple disaccharide. This is lactose. What we can do is we can add water to the system. And we do that, basically what we're going to do is we're going to break that disaccharide down into 2 monosaccharides. And so you have enzymes in your body that are going to help you break down lactose, but we still are going to require a water every time we break one of those polymers apart. Do so. And so basically, why is this important? Well, this is a picture of me when I was little. And my favorite food, I know this is gross, when I was growing up, was the filet-o-fish sandwich from McDonald's. And so basically, when I was eating that filet-o-fish sandwich, it was made up of a number of different polymers, like the polysaccharides in the starch in the bun, and the proteins that are found in the fish, in the filet-o-fish. And so basically, when I took this in and ate it, in digestion, I was breaking that back down into its monomers. But then I was putting those back together again using dehydration reaction to make the proteins that are found in my hair or my skin or all of the cells of my body. And so you literally are what you eat, thanks to polymers. But again, they wouldn't be formed unless we had the building blocks, and those are called monomers. And I hope this is helpful.